Hello, welcome to Zigmatech Learning Hub. I will be your instructor for physics. For this class, we are going to be taking our exercises from Examguide app. If you don't have the application already installed on your device, I will want you to download the app in order to follow along in this class. Examguide is a leading educational app that helps students prepare adequately for various exams like UTME, post-UTME, WEAC, GCE, KCPE, IJMB, JUPEB, KCPE, BECE, JSCE, NCEE, NECO, etc. You can download the app from www.examguide.com or Google Play Store. Please subscribe to our channel and turn on the notification bell and get updated on new videos. Are you ready for this class? Okay, let's get started. Have you wondered why some objects float in water and why others don't? Have you wondered the science behind immersion and floating? These and many more will be introduced and fully explained in this class as I welcome you to this topic titled Fluid in Rest and Fluid at Rest. By the end of this lesson, you should be able to define volume, density, and relative density. Then solve problems on density and volume, and also state Archimedes principle, law of flotation, define Upthrust, and solve problems involving Upthrust. And finally, solve more problems on relative density. Let's get started if you are ready. When we talk about volume, we are talking about a space occupied by a matter. The space in your room, the corner in your room being occupied by your chair. The space in the place you are standing occupied by the screen you are using to watch me. That space which is occupied is what volume intends to look at, provided that the height or the thickness of that particular object is considered. So that is what volume is all about. Now, when we talk about density, we are talking about the mass of the object divided by the unit mass. That means when you are talking about density, we are considering the mass of the object and the unit volume of the object which it occupies. So we may say that this symbol is rho, which is a symbol used for representing density, and this symbol is giving us mass over volume. So if you are talking about density of water, so we are going to look at mass of water and then the volume of the water. So that is what density is all about. And it's also there written on the screen, the mass of a substance and the unit volume of the substance. Then when we talk about relative density, we are talking about mass of a substance divided by mass of equal volume of water. Then density of a substance and density of water. That mass of equal volume of water is a very important term when you are talking about density and its relative density, which we are going to be extracting as we go further in this lesson. But remember the formulas which is written on the screen and this relation written here, because they are going to help us as we move going forward in this topic. Now, using those relations which I have given, we are going to look at the first question we have here on the screen. It said the first problem we are going to solve is a piece of cork of density 0.25 times 10 raised to the power 3 kilogram per meter cube float in a fluid of density 1.25 times 10 raised to the power 5 kilogram per meter cube. It said what fraction of the volume of the cork will be massed? Okay, so when we are looking at this question, we are looking a little bit of the issue concerning flotation. Now, first of all, let's look at the terms given here. Then we apply the principle of the flotation before this question can be fully solved. A piece of cork of density. So let's say the density of cork, I'm using C as the density of the cork. And I'm giving it as 0.25 times 10 raised to the power 3. Remember that this can be written as 2.5 times 10 raised to the power 2. Yes, because this point we move to one side and that is -1. Then take off from 3 and that is going to be 2 left. So, but I'm using this one, kilogram per meter cube. So that is the density of cork. Then remember that for us to be able to fully explain this density of the cork, we have to say that density of cork is going to be mass of the cork all over volume of the cork. Remember? Then, let me call this one the first relation. Now, I can do this by saying, instead of writing this, density of cork is this, I'm going to put it, I'm going to have 2.5 times 10 raised to the power 2, which is equal to mass of cork all over volume of cork. Now, there was no mass of the cork, so I'm going to say that mass of the cork is going to be, this is 2.5 times 10, then, so this is going to be 250 times the volume of the cork. So this is the further of the relation. So at this point, I started with the cork from this relation, but this one is the main formula. Then you can model it based on the question you are given. So this is density of the cork. Density of cork is mass of the cork over volume of the cork. So I converted this back to ordinary number to have 250, because 2.5 times 100, because 10 raised to the power 2 is 100. So we have 2.5 times 100, and that is going to give you 250. And that is how I got this 250. Then if I clear this fraction, I have mass, this is going to be this multiplied by this, which is the first thing concerning the cork. Now, it said float in a liquid of density. And this is floating in a liquid of density. Okay, let me. So then when we talk about the density of the liquid, we now say that density of liquid is also mass of the liquid all over volume of the liquid. I'm modeling this same formula again to accommodate this liquid. So what do we have there? We said that the density of liquid is 1.25 times 10 raised to the power 5. So I have 1.25 times 10 raised to the power 5 is equal to mass of the liquid all over volume of the liquid. So in this case, I'm going to treat this to bring it back to a normal number, probably for easy solution. So I have 1.25 times 1, 2, 3, 4, 5. I hope you understand that. So this is 10 raised to the power 5, 1, 2. Cancel this. We have 1, 2, 5, and 3 zeros, 1, 2, 3. That is the relationship. I have 1, 2, 5, 1, 2, 3 is equal to mass of the liquid all over volume of the liquid. So mass of the liquid is 1, 2, 5, 1, 2, 3 volume times this. So this is the mass. This is the mass of the liquid, while this is the mass of the cork. Now, what fraction of the volume of the cork will be immersed? The mass of the cork given as this is going to be 250 multiplied by the volume of the cork is going to be equal to the mass of the liquid, which is 125,000, and the volume of the liquid. So in order to find the fraction of the volume of the cork that was immersed, so I have to divide 125,000 by both sides, and that will cancel this. Then also I'm going to divide VC on both sides. So VC will slash it. We'll have 250 all over 125 is equal to volume of the liquid all over volume of the cork that was immersed. So in this case, when you cancel the zeros here, then you now have, this should be 500. You have 125,000 when you divide it by 25, that means this is F1, this into this is 500. So you have the volume of the liquid with respect to volume of the cork is 1/500 meter cube. And this is the fraction of the volume of the cork that was immersed in this liquid. So moving on this number 2, we said that the density of 400 meter cube of palm oil was 0.9. So density of palm oil, I'm going to use P as palm oil, is given at 0.9 kilogram per meter cube. That's the density of palm oil before frying. And then this is before, I'll use B as before, density of palm oil before frying. Then density of palm oil after frying is given as 0.6 kilogram per meter cube. Now, assuming no loss of oil due to spillage, calculate its volume after frying. Now, that statement is very, very important. They said, assuming no loss of oil due to spillage, that means the mass of the oil could not be reduced. That means the mass is the same before and after frying. If that condition is highly obeyed, we are going to calculate its volume after frying. Now, in this case, remember when we talk about density, we are talking about the mass of the substance per unit volume of the substance at that time. So I'm going to start with the density of palm oil before frying is given as, is given as mass of the palm oil over volume of the palm oil, all right? This one is before. I'm using B to say before. This one is different. So if I substitute the values here, I don't know the mass and I don't know the volume. I'm looking for the volume, but we can make a principal statement or fact concerning the mass going forward in order to be able to simplify it. So this is this, which is 0.9, which is equal to mass of the palm before all over volume of the palm oil before. Therefore, mass of the palm oil before frying is given as 0.9 volume of the palm oil before frying. Now, in this case, we are going to also consider write this same for the density of this oil after frying. So I'm going to put it down here. So I'm going to say density of the palm oil after is equal to mass of the palm oil after frying all over volume of the palm oil after frying. And this is going to be mass of the palm oil after frying is going to be 0.6 volume of the palm oil after frying. Okay, now in this case, we are going to make an assumption that the mass of the palm oil before frying must be the same thing as the mass of the palm oil after frying. Then, in this case, we are going to be able to solve it. So the mass of the palm oil does not change. So, but then the density of the palm oil was this before frying. So we know the volume of the palm oil before frying. And this is the volume of the palm oil before frying. And it was given as 400. So I'm going to have 0.9 times 400 is equal to 0.6 volume of the palm oil after frying. Therefore, we say calculate the volume after frying. We are going to divide both sides by 0.6. So volume of the palm oil after frying is going to be this. If you use your device, so you have 360 divided by 0.6. And that is 600. So volume of the palm oil after frying it is going to be 600 meter cube. So that is it. All right. We are moving on to the next one. Now, we also have a problem on volume and density here. It said the density of an ice is 0.92. What fraction of the volume of piece of ice will be submerged when floating in water? In the same principle will be applied in solving this problem. Now, when we talk about the question on relative density, we said that what is the density of a field of relative density 0.2, while the density of water is this. So at this point, we have that relative density according to the question given, according to the relation given earlier. We said that the relative density is going to be mass of the substance over mass of equal volume of water. So in this case, say what is the relative density of, what is the density of a field of relative density this? Also in this case, remember that in this question, there was no question concerning mass. Therefore, I'm also going to give the second relation of relative density, which says that it is the density of a substance all over density of water. So this is going to be the one that will help us truly to solve this problem. So I will work with 0.72, which is the relative density of the field. Then I am looking for the density of the field. I'm using F to represent density of field all over 1,000, which is the density of water measured in kilogram per meter cube. So density of field is going to be 0.72 multiplied by 1,000, and this is 2 goes. So density of field is 720 kilogram per meter cube. All right, still on a few problems on relative density. We have another problem here. All right, a density of bottle has a mass of 0.04 kilogram when empty, a mass of 0.20 kilogram when some quantity of steel ball bearing is added to it, and a mass of 0.2 kilogram when the remainder of the bottle is filled with water. If the density bottle weighs 0.1 kilogram when filled with water, calculate the relative density of the steel ball bearing. This is really a practical question, and we are going to take them step one after the other. Now, at this point, we have the density of the bottle measured when it is empty. So I'm going to call that one M1. That is density of the bottle when nothing was put in it, and 0.4 kilogram, right? Now, a mass of 0.220 kilogram when some quantity of steel ball bearing is added. So you see at this point now, what we are going to have there is mass of the density bottle plus mass of the ball bearing that was added into it. So I'm looking at these two, as this one as M2. So when both the density of the container and both the mass of the container and the mass of the ball bearing that was put inside it, you understand? So and that is 0.20 kilogram. Now in this case, if you have this kind of problem and you are asked to find the mass of the ball bearing, what do you think should be the best approach? This is the mass of the ball bearing and the mass of the empty vessel. Then this one is the mass of the empty vessel. To be able to find the mass of the ball bearing put inside it, you have to say 0. This, then minus this, in order to find at least the mass of those materials. Then the next one is the mass of 0.24 kilogram when a remainder of the bottle is filled with water. So the remainder of the bottle is now filled with water. So I'm going to call that one M3. And that is going to be 0.24 kilogram. Now, if the density bottle weighs, all right, you see that now. Okay, you see that if the density bottle weighs 0.1, that is really where it is. The first mass, which is 0.04 kilogram, is the density, is the mass of the density bottle when it is empty. Now, if the density bottle weighs 0.1 kilogram when filled with water, so I will call that M4, when filled with water, 0.1 kilogram. Now, what is the question? Calculate the relative density of the steel ball bearing. First, the first question you should ask yourself is, what is the mass, what is the relationship of the relative density? Now, the relationship of the relative density is mass of the substance or particle of the body. At this point, mass of steel ball bearing all over. There is this statement, which is mass of equal volume of water. Now, very important thing you have to note about this statement. Mass of equal volume of water. We are not talking about mass of water anyways. But remember, when water was poured inside a ball bearing, there is a displacement of water, or should I say the upthrust. So the mass of the ball bearing is equal to the mass of the water displaced in the container. Now the question is, how then do we find the mass of the ball bearing? So we now start with the first one, which is the density bottle of its mass when it is empty. You see, when nothing is inside it, is 0.04 kilogram. Now, a mass of 0.20 when some quantity of steel bearing is added. So at that point, what do we do in order to get the mass of the steel ball bearing? We are going to have then one more thing, which is M3. M3 is when some quantity is filled, when the rest of the ball bearing of the container is filled with water, which is 0.24. And we are not looking for the quantity of that water. We are looking for the mass of the ball bearing. So to find the mass of the steel ball bearing, we have to subtract the mass of 0.20 when quantity was filled from the mass of the empty bottle. So we have 0.20, which is M2 minus 0.04. Then when we have this done, we have 0.16 kilogram, and that is going to be the mass of the steel ball bearing. Now, the most technical aspect of this topic is the one down, because it's a practical question. So what you have to do first is to find the mass of the water, the total mass of the water that filled the whole container when no substance was inside the container. And how to achieve that is going to be 0.1, that is M4. M4 is going to subtract the mass of the bottle when it is empty. So it's going to be 0.1 minus 0.04. So you have 0.1, 0.04. So you have 0.0. So this is the volume kilogram. So what this mass is talking about, okay, let's finish the rest of this problem. Then when you have 0.024 minus 0.2, we now have another quantity of water, which is 0.24 minus 0.2, which is going to give you 0.04. You see now, this is in kilogram. Then this is the quantity of water which filled the whole container. Then this is the quantity of water which was used to fill the container when some ball bearings were inside it. Then there is another mass we need, and that mass is going to be the mass of the volume of water, which is going to be, that is the volume of water displaced, which is equal to the mass of the ball bearing. And that is going to be when you say 0.06 minus 0.04, which is going to give you 0.02. So if these are all taken care of, we are now going to say that the relative density of this is going to be 0.16 all over 0.02, and then that is going to be 0.8. And remember that relative density does not have a unit, and that is the answer. Now, in this case, Archimedes principle. Most of the calculations we are solving are based on this principle, especially Archimedes principle and law of flotation. It says Archimedes principle states that when a body is totally or partially immersed in a liquid or fluid, it experiences an upward force. It experiences an upward force which is called upthrust. And that upthrust is equal to the volume of the fluid that was displaced. Now remember, if you have water poured inside a bucket, then you put some clothes inside it. What do you think that will happen to the water in the bucket? It will rise a little. And that rise in the volume of the water is called the volume of water displaced, which is as a result of the object or the substance you put inside water. Remember the principle of the Eureka can, or what we call the displacement can. Now we'll get back to that, but then when we talk about the law of flotation, we say that it states that an object will only float in a fluid when that same upthrust exerted upon it by the fluid in which it is immersed is equal to the weight of the object displaced. So it's still the same thing. For a body to be able to float, it means that that object have to displace a volume of water which is equal to the upthrust which the liquid is putting on it. We are going to look at some of the conditions for this flotation which led to the building of ship and some other objects using water. Now, watching this little video clip, you see what I'm saying. Now, look at that yellow object according to Archimedes principle. If you look at this yellow object, what you are seeing is that when it was immersed in the water or liquid, then some water was poured out. When it is immersed in a liquid, some water was poured out. Look at it as it's going in. Some water are pouring out. Now, the quantity of water which is being poured out is called the amount of water displaced, and that is equal to the upthrust on the body, on the yellow body. Let's check it again. As you see that as it's displacing inside water, then some quantity of water is being displaced on the beaker, and that is exactly why he stated it clearly that it experiences an upthrust, and which is equal to the weight of the fluid that was taken out of this beaker. This beaker now, the quantity of water taken from this beaker is equal to the weight based on the upthrust. Now, look at this clip also. You are seeing a body floating. And remember what the law of flotation stated. That body was supposed to sink, but it didn't. It now decided to float. Why? Because according to the law of flotation, it stated it clearly that the object can only float when the upthrust exerted by this fluid, in this case this is water, the fluid here now is water, the upthrust on this in this water is equal to the weight of the fluid displaced. Now, there are a few factors that affect flotation. There are some few factors. Number one is the density of the liquid. Now, it says that density of a body must be less than its liquid whenever it is immense. So when we're talking about it being less, that means the liquid must be more dense than it. Then in that case, you say that the body can be able to float. If the density of object is denser than that of the liquid, it will just sink. So when you put body inside liquid, it will just sink. But when the liquid, or let's say water in this case, is more denser than that substance, then it cannot. Another condition for flotation is the shape of the body. And that is why ships or canoes are shaped in that manner, so that they will be able to displace their own weight whenever they are immersed in a liquid. And these are two conditions which has led to this improvement in aquatic transportation or water transportation. Now, upthrust itself, this is the weight of volume of water displaced. When an object is completely immersed, it is given by U equal to VPG. So the upthrust, there are few relationships about upthrust, but then this one is the V, and then now this is the volume of the object, and this is the density of the liquid, which is very important, and this is acceleration due to gravity, as it is shown there on the screen. Remember that when upthrust is acting on, if we have this as a containing vessel and then you put this object here and this is liquid, let's say for example this one is completely immersed, then the upthrust is going to be pushing upward. You know, the upthrust pushing upward. Sometimes this body will not be completely immersed. This is complete immersion. But sometimes they will not. What will happen is that some part of the body will be outside while some part of the body will be immersed. In this case, we may say that a volume of the body was immersed. In that case, they say 2/3 or 4/5 of the body immersed. In that case, this volume will no longer be a full volume. It's going to be, upthrust will now change to be, let's say, 3/4V, density of the body and acceleration due to gravity. These are going to be used in subsequent problems as we go further. Now, look at a question here. There is a question on upthrust, and then this is not the only formula or relation for upthrust. Another formula for upthrust is this, that the weight of objects in air minus the weight of objects in liquid or fluid or water, whatever it is. What this is saying, this is the first or general relation for upthrust, while this is also there, depending on the question you are to solve. Now, why this one? Why this formula? Because what upthrust is saying is this: when you put a body, any body, let's say this marker, you weigh the mass of this marker in air by using a spiral spring, the mass or weight recorded will not be the same weight is going to record when you put it inside a liquid when it is totally immersed. In that case, the change in the weight of this body when it is in liquid and when it is measured in air, the change in them is what we call upthrust. Now let's look at this problem on the screen. So the first question there said a body weighs this 0.3 in air and 0.25 when fully immersed in water, and 0.27 Newton when fully immersed in a liquid. It said calculate loss in weight in water. Of course, So weight in air, I'm giving it as W1 is 0.3 Newton. And then weight when fully immersed in liquid is W2 is 0.25. So upthrust is weight in air minus weight in liquid. Upthrust is given as 0.3 minus 0.25, and upthrust is, this is 0.05 Newton, because upthrust is in weight, and that is it. Now, its relative density. What should be the relative density? The relative density is going to be the weight in air and the weight when totally immersed in a liquid. So the B part, this is A part, and B part is going to be its relative density. Relative density is the weight of the object and when it is in water, and that is 0.3 over 0.05. Then if you 0.3, 0.5, and that is 6. Okay, now the relative density of the liquid, when we talk about relative density, we are talking about the density of the liquid over density when it is fully immersed in water. Now, relative density at this point is going to be the upthrust in liquid over upthrust in water. So upthrust in liquid is going to be, remember the question that said that when fully immersed in water is this, and 0.27 when fully immersed in a liquid. So it's going to be the mass in air minus the mass in the liquid, and that is going to be 0.3 minus 0.27, and this is 3. So this is 0.03. Now, the relative density in liquid and relative density in water. I mean, the upthrust in liquid and upthrust in water. So the upthrust in water, as we said, was 0.05, because you have to say 0.3 minus 0.25. And this is going to give you 0.05. It's going to be upthrust in water, and this one is upthrust in liquid. So relative density can be upthrust in liquid over upthrust in water. So this is 0.05. And that is going to give us 0.6. And that is relative density. That is the relative density of the liquid. We've come to the end of this class, but before we go, let's take some exercises from Examguide app. You say the weight, an object weight 60 Newton in air and 48.2 Newton in a certain liquid and 44.9 Newton in water. You say calculate the relative density of X. For us to be able to calculate the relative density, remember, relative density is upthrust in liquid over upthrust in water. So what is the upthrust in liquid? Upthrust in liquid is the mass or the weight of the object in air subtracting from the weight of the object when it is immersed in that liquid. So if you look at this question, the weight in air is 60, and then the weight when immersed in a liquid is 48.2. So we are going to say 60 minus 48.2. So this is 8, and this is 59. So you have 59 minus 48, and this is 1. This is 11.8. Therefore, the relative density is going to be 11.8 divided by The next one is the upthrust in water, and the upthrust in water means the weight in air minus the weight when immersed in water, and that immersing in water is 44.9. So we are going to say 60.0 minus 44.9. So we have 60 minus 44.9. We have 15.1. So this is 15.1. So the relative density of this object is going to have 11.8 divided by 15.1, and that is 0.782. 0.78. So we have 0.78 approximately. So which is going to be D. The option there is D. This one is about viscosity. Okay, it said an object weighs 10 grams in this number. The next question, an object weighs 10 grams immersed in a liquid displaces a quantity of liquid. If the liquid displaces 6 Newton, determine the upthrust on the object. So when it is weighing 10 Newton in a liquid. So look at, he said an object of weight 10 Newton immersed in a liquid displaces a quantity of liquid. If the liquid displaces the, okay, what you are going to do is 10 subtracting by 6, because remember that upthrust is weight in air minus weight in liquid. So if you have this in place, we say that 10 subtracting from 6 is going to be 4, and the option is D. Now, we also have another question. It said a body weighs 14 in air, partially immersed in water. If the mass of water displaced is equal to, is displaced in the process is 20 grams, calculate the upthrust on the body. Okay, let's check a little something different, because it has been upthrust all this while. No, this one is, no. Okay, see this one. He said, what is the density of a fuel of relative density? 0.25, 0.72. Oh, see, I think we have solved this before. All right. A body of volume 0.04 meter cube is immersed in a liquid of density 980 kilogram per meter cube with 3/4 of the volume submerged. Calculate the upthrust. All right. This question is this: U is equal to V, density times acceleration due to gravity. But in this case, the one that was immersed in the fluid is just 3/4 of the whole volume. So I'm going to have this as going to be 3/4 times. The volume there is given as 0.046. 0.046 times. The density of the body in this case is 980 times acceleration due to gravity, which is 10. So U is going to be 3/4 is 0.75. So you just pick up 0.75 multiplied by 0.046. Then multiply it by 980. Then multiply it by 10. We have 338.1. Yes, and that option is D as well. 338.1. Yes, the option is D. So everything here, U is going to be 338.1 Newton. Thank you for participating in today's class. You can practice more questions using the Examguide app. The app scores and gives a detailed explanation of all the questions at the end of your practice test. You can learn a particular topic of interest with different modes like study mode, mock mode, and practice mode. It also has other features that makes learning fun. It is a must-have for all serious students. Download from www.examguide.com if you don't have it yet. See you in the next class. Don't forget to subscribe to our channel, hit the notification bell, and share the video to people that will benefit from it. Bye.